Reality check. We're about to go deep. These topics don't play nice, and they require 100% of your attention to handle. If you're here to just browse, it's going to get overwhelming fast. Only continue if you're serious enough to do the heavy lifting. Ready? Let's get to work.
Hey everyone, welcome back to the channel. I am your physics buddy, and today we are leveling up our electricity and magnetism game. We have mastered forces and field, and now it's time to talk about the why behind the motion, electrostatic potential and capacitance. In this session, we are breaking down exactly what potential energy looks like in an electric field and how capacitors act as an ultimate energy tank for our circuits. Whether you are preparing for an FRQ or just trying to wrap your head around voltage, I have got you covered. Now, if you are just joining us, remember that we have already covered several core units of AP Physics 2 curriculum right here on the channel. So make sure you check those units out to keep your foundation solid.
So today's session will start with electrostatic potential or electric potential, and we'll figure it out that what is the key component which is responsible for charge storage in capacitors also. So that will going to be the topic for the next class. But in today's class, we're going to talk about what is electrostatic potential. So in order to understand electrostatic potential, there is a small question for you that why lightning hits specifically a particular building, not all the other ones. Why this specifically particular one? So this is the question that we're going to answer, and let's see how we can answer this particular question by understanding what is electrostatic potential. So this is going to be the second part of electrostatic, to be precise, from the unit where charges are at rest. So whenever we try to move a charge from one particular location to another particular location, if the charge is moving against some force, it will develop some electrostatic potential. So these are going to be the topic. We'll start with electric potential energy, then we'll talk about what is electric potential. We'll see the relation between electric field and potential as well, then equipotential surfaces. So whenever we define electrostatic potential or potential energy, we need to understand this fact that potential energy is defined as work done by conservative force or conservative force field. So we have to understand this fact that in this universe, we have only 4 conservative forces. It all started in grade 11th, where we talk about gravitational force. It is one such conservative force. Then we talked about spring force. This is again one such conservative force. Then we talked about electrostatic force. So electrostatic force is also a conservative force. And then we have nuclear forces. So only because of these 4 forces, we define potential energy. So first 2 forces, that is gravitational and spring force, we have already studied in grade 11th. But now we'll be talking about electrostatic force, potential energy, or you can say the potential energy due to electrostatic force. And the last force, nuclear forces, potential energy due to nuclear forces, we are going to talk about it in modern physics. So these are the number of forces we have only, and these forces are responsible for potential energy in a given system. So potential energy is defined for electrostatic forces only, which is conservative in nature. What does it say? It says that change in potential energy is negative of work done by electric force. That is this. So whenever we are talking about potential energy, we are only talking about change in potential energy, and here the change in potential energy is defined by negative of work done by conservative force. Now, if you try to recollect that what is conservative force or what is work done, so work done is force into displacement. So if there is a small change in potential energy we are calculating, so that small change in potential energy is nothing but negative of work done, negative of force times displacement. So in order to find out the potential energy here, what we used to do is we used to integrate this situation. How we can do this? Just try to understand it this way. So forces, you already studied this K Q1 Q2 by R square. Or here I can write it as x square, negative of integration. Now the K, Q1, Q2 are supposed to be constant. So they will came out of integration thing. So change in potential energy can be given as K Q1 Q2, that 2 of negative is times integration of dx by x square. So once we integrate this situation, so what we are going to get? -2 plus 1 -2 plus 1. That only. So this will give us potential energy or change in potential energy as K Q1 Q2 by R. We are integrating it from 0 to R, that too in negative. So this is the relation for change in potential energy that we are actually going to use to solve or to find potential of a given system. Negative of KQ1 Q2 by R. Now, how this formula came? This formula came from the definition of potential energy, which is defined by negative of work done by conservative forces. So, what is the electrostatic potential energy for multiple charge system? That is
One
going
second,
to be
sir. One
the.
second.
You are writing this?
Okay, sir. Yeah.
Now, this was the potential energy due to system of charge. Now, what if we have multiple charges in our system? For example, suppose there is a square surface, and at this surface, at all the edges, there are four charges placed. Let's say Q1, Q2, Q3, Q4. Now, if we have to find out the potential energy at the center of the square, let's say at point C, so what it is going to be? So, potential energy is going to be sum of potential energies of due to all the charges. So, it is going to be U1 plus U2 plus U3 plus U4. Or you can write it as now at the center, if we just try to understand, let's say there is some charge Q naught place. So potential energy at the center is going to be, we need to understand that what is the distance here. If the side length is A, so this distance is going to be A over root 2. We can easily find it out. This distance is going to be A over root 2 if the side length of the square is A. So if we try to write the sum of all the charges or potential energies of all the charges due to all the charges, it is going to be K Q1 Q naught over A by root 2 plus K Q2 Q naught over A by root 2 plus K Q3 Q naught over A by root 2. And at last, K Q4 Q naught over A by root 2. So if we try to solve this, we'll get change in potential energy for this given particular system is going to be K Q naught root 2 times by A into Q1 plus Q2 plus Q3 plus Q4. So what's important here is to understand is that whatever force is acting between the charges, first of all, it is going to be responsible for the potential energy. And then if we have to find the potential energy of the system, we'll add the potential energy of individual pair of charges for the given for the given system. In order to understand this particular relation to a greater extent, let us try to see that how much work actually is required to done to form such a configuration. But as of now, try to remember the relation that in order to find out the net potential energy, we'll add to the potential energy due to all the possible pairs of charges in the given system at a given point. Here, there were four pairs that we can actually observe, and we have written potential energy due to this four pairs only, and this is going to give us the net potential energy. Remember, this is going to definitely come into the exam, and from the exam's point of view, this particular topic is again very important. So let's move ahead and try to understand different other factors as well. So here is given a question, and the question says, what is the total potential energy of the given system? Now, when we are going to find out the potential energy of such given systems, we have to find out the given number of pairs. Or you can say we have to understand that how pair of charges, how many number of pair of charges are going to be take place there. So in order to do that, what we can do? There are going to be three pair of charges. Let me mark it as point A, B, C. So there will be pair of charge A and B, pair of charge B and C, and pair of charge A and C. So there are total three pair of charges, right? So if we try to find out the potential energy, we can simply say that the total energy of the system is going to be all the three pair of charges. So it is going to be K Q1 Q2 over R plus K Q1 Q2 over R plus K Q1 Q2 over R. As you can see that the charges are equal in magnitude for all 3 points. So we can simply write Q1 and Q2 as Q and Q. So what we are going to get? We're going to get 3kq square over r. That is going to be the change in potential energy of the whole system. Like as simple as that. Not that much difficult. You just have to understand the basics and you'll be able to find out the potential energy of the given system. Is it clear? Did you understand it?
Yes, sir. Yes, sir. I was muted.
Now, another system, again, we have to find out the total energy of the system. Now, how we are going to do this? That is an important or interesting question. As the system of charges has three charges, that too placed in a straight line. So when we are going to form the pair of charges, so first pair we are going to have is this, second pair we are going to have is this, but the third pair we are going to have this, the first and third charge. So this is what you have to understand here. Whenever we are going to form pairs, pairs will be formed based upon the number of charges. So it is going to be 1 and 2, 2 and 3, 1 and 3. So these are the three pairs that are going to be formed there. So the change in potential energy is given by K Q1 Q2 by R. So Q1 Q2 both are same. So I can write K Q by R plus. Now between 2 and 3, it is going to be K Q over R. Between 1 and 3, it is going to be K Q over 2 twice of R, because the distance between the first and third charge is twice of R. That's it. This is what we have to find. So KQ square over R can be taken out as common. It is going to be 1 plus 1 plus 1 by 2. So it is going to be 2 plus 1 by 2, that is 3, 5 by 2, KQ square over R. So this is how we will find out the potential energy for a given system having charges placed in a straight line like that. Again, try to remember the actual relation, that how we are actually going to find out potential energy. Potential energy in a given system is due to the number of pair of charges that are present there. Here, the number of pair of charges present there, we have is simply seen 1, 2, 2, 3, and 1, 3. So you two just have to figure it out that way only. All right, then let's move ahead. So this is again a simple question. But now, if you have to find out the total potential energy of the given system, you have to find out the number of pair of charges. That is again the very important part about finding potential energy for given system. So how many pair of charges do we have here? Think and tell me.
2.
Pair of charges. Like how many pairs from these given four charges we can form? Different pairs. How many combination of different pairs we can form?
4.
Not four. We are going to have six pair of charges. Just look at it. 1, 2, 2, 3, 3, 4, 4, 1, 2, 4, 1, 3. Like we have the pair of charges sideways as per the sides and also diagonal wise. This is also possible. So all the pair of charges that are present there, we have to consider each and every one. So when we are finding the potential energy, change in potential energy of the system, or the total energy of the system, because the system will only have potential energy, it is going to be due to all the four pairs, six pairs. So for the sideways or the side of the square sides charged particles placed, so we can say it is going to be KQ square over R square plus KQ square over R square plus KQ square over R square. Not R square, it should be R. R square is the electric field. Electric field is supposed to be kq over r square. So these are due to the four pairs, this one. But what about other two pairs? For other two pairs, the distance is going to change. Again, it is going to be kq square over distance. The distance between the diagonal. What is the distance? It is going to be root 2r. So I can write it as root 2r plus kq square over again root 2r. So these are the six possible number of pair of charges we can have in this given configuration, and all the six pairs will be capable of producing some potential energy or generating some potential energy. So here it is going to be 4 kq square over r plus twice of kq square over root 2r. In order to solve it, we can take few things common. Kq square over r can be taken out as common, and what we are left inside is 4 plus root 2. So this is going to be our answer. Again, calculation is a key thing here. We need to be very good with our calculations. And if you're going to do any mistake, we still get some marks if it is FRQ. Otherwise, no. If it is a multiple choice question, we have to be very accurate with our answers. If we are accurate, we got to have the answer, we got to have the mark, otherwise, no. So make sure all these points in mind while solving such problems. Just remember the process. First, you have to find out how many number of pair of charges are there. Then just form those pairs, find potential energy, and potential energy is given by KQ over R. KQ1, Q2 over R. That is the relation for potential energy. KQ1, Q2 over R, where R is supposed to be the distance between the two charges. And how this formula came, we just saw the derivation in the very first slide. Let's move ahead. So there is another charge, another system, but what we have made a change in the system, that this charge becomes negative. So what will happen if this charge becomes negative? Let us try to figure it out. Before that, let us just mark the pair of charges that we are going to have. Again, there are 4 charges placed at the vertices of the square. So the number of pairs we're going to have is the same as that of the last question. 1, 2, 2, 3, 3, 4, 4, 1. This is which is placed on the sides. And when you're talking about the diagonal, it is going to be 1, 3 and 2, 4. So let us try to figure it out what the potential energy will come out to be. The potential energy is going to be first for 1, 2, kq square over r. For 2, 3, it is going to be negative of kq square over r. For 3 and 4, again it is going to be negative of kq square over r. For 4 and 1, it is going to be kq square over r, like that. So the thing will become 0. Similarly, for the diagonals, it is going to be for 2 and 4, it is going to be kq square over root 2r. And for another diagonal, it is going to be negative of kq square over root 2r. So you can see by changing a one charge to negative q, the potential energy of the system becomes 0. Everything got cancelled out. The total energy of the system is going to be 0. And how we got to know about this? By using the relation for potential energy of a given system. So this is again an important problem, and we have to think that way only, that how this particular problem gives us the potential energy. Now, this is an interesting question. You have to understand that how this question is actually being solved. The question says how much energy is required to change the configuration. So in order to find out how much energy is required, what you have to do is you have to find out the potential energy of this system. Similarly, you have to find out the potential energy of this system. Then whatever you are getting from both the equations or both the figures, just subtract it. And whatever change you are getting there, that is going to be the total energy required to change the configuration. I hope you are cleared with the concept that what exactly we have to do here. So we have already found the energies of these two figures in two different questions. The energy of this configuration is 3 kq square over r, whereas energy of this configuration is 5 by 2 kq square by r. We'll simply substitute the values here. So this is 3 kq square over r. This is 5 by 2 kq square over r. Now just look at the values of u1 and u2 and tell me whether the potential energy of the system has increased or decreased in the case from 1 to second configuration. Think and tell me, is the potential energy of the system decreased or is it increased? I don't know, are you there?
Decreased.
Yeah, correct. So if we talk about the change in potential energy, it is going to be 3 kq square by r minus 5 by 2 kq square, which is going to be kq square over 2r, like half. This is 3, this is 2.5, so we are going to get half. So this much energy is required. This much energy is required to change the configuration. That is what we have to understand. So all these things which we are talking about here is related to the electrostatic potential energy, and they are very important. Now think about this problem and tell me what should be the preferable answer.
Decreases.
Mm, it depends. Although, if you just look at it from the first go, you'll definitely go with decreases. But we have to understand this fact that it also depends upon the separation. Apart from separation, it also depends upon the magnitude of charge. As we are talking about potential energy here, potential energy is a scalar quantity. And for all those scalar quantities, what we actually understand here is that their nature are always considered. So if nature is considered, like if it is positive or negative, if it is considered, so it doesn't depend upon only the distance between the charges. It also depends upon the nature of the charges. So the answer of this question is that it may increase or decrease. That is what, again, an important point to keep in mind. So make sure that you remember this point. Now let's talk about what is potential. Potential energy is different. Potential is different. So potential is defined by potential energy per unit charge. What is the potential energy per unit charge? You can simply find it out. Like for example, potential is represented by V. It is equals to potential energy per unit charge. We know potential energy is K Q1 Q2 over R. So if we just divide the whole thing with Q1, we'll get potential as K Q over R. This is the potential relation for potential. Now let us try to memorize all the relations we have studied so far in this chapter. It all started with force. So force is supposed to be K Q1 Q2 over R square. Then we talked about electric field. Now in the electric field is given by due to one charge only, so it is going to be K Q1 Q2 over R square. Then we talked about potential energy, which is going to be K Q1 Q2 over R. Now we are talking about potential, it is going to be K Q1 over R. So you can see that how the formula changes as we move from one physical quantity to another, and this is only based upon the definition of these particular quantities. So these are the given number of relations we have studied so far in this particular chapter. But apart from this, we are going to talk about some more. Like when we're talking about capacitance, there are some different things as well. We'll definitely talk about them. So the unit of electrostatic potential is always given as volt, and this volt is also written as joules per coulomb. Because we know energy is given in joules, charge is given in coulombs. So it can be joules per coulomb. Also, we call it as volt, like the potential. Battery must have some potential, and that potential is measured in volts. So we have to understand this fact that only changes in potential energy can be measured. When we are talking about potential, we cannot measure potential of a given point, but we can measure the change in potential of a given point. So whenever we are talking about that there are 2 point charges or there is 1 point charges, it has been moved from one point to another point. So during that movement, during that motion, we cannot actually measure the potential of individual points. But what we can do is we can measure the potential of, or you can say we can measure the potential difference of both the points, which is going to be represented by delta V, which is always equals to VV minus VA. And this is equals to potential energy at point B minus potential energy at point A divided by charge, which is going to give us what? Which is going to give us negative of work done by charge. So again, everything is from its definition part only. Remember this relation. This relation is very important. We're going to use this so many times in numericals. Conventional reference is kept at infinite separation from the charges to discuss potential at a point. So if we have to find out the potential of a given point, we'll take a conventional reference, and that reference says that at some infinite separation, charges can be taken as to be at infinity. So will R automatically become 1 over infinity? So that is a different case. We'll talk about that as well. So just try to read the question and think about which should have the greatest net electric potential And we have to place them according to their values, like which one is the greatest. We have to put the greatest one first.
C B A.
See, we have to find out electric potential, net electric potential. So net electric potential is nothing but negative of work done per unit charge, right? Now the question says that what is the electric potential produced at point B by two protons? So there are two protons. So these two charges are protons, so I can mark it as QQ. Here also it is going to be QQ. It is also going to be QQ. So if you have to find out the potential at point P for the first problem, it is going to be potential due to first charge plus potential due to second charge. What is the relation for potential? KQ over R. So the first charge, it is going to be KQ over D. For second charge, it is going to be again KQ over T. So this is going to be for the first figure. Now for second one, potential at point B is again going to be Q1 plus V2. V1 is given by KQ over D plus V2 is given by KQ over R or small d. For this relation as well, potential is going to be V1 plus V2, which is equals to KQ over capital D plus KQ over small d. If you just try to look at the values, as we already understood this particular fact that potential is a scalar quantity, so it doesn't matter how the charges are being placed. What matters is at what distance they are placed. If they are placed at the same distance, just like the other things, so it's true, it is going to be same. So in all the three cases, potential is same. We have to understand this thing. That potential is not something which depends upon that how charges are being placed, but it depends upon that how, and you can say it depends upon that at what distance the charges are placed. If they're placed at same distance and we are finding the potential at a given point, they are going to be same, just like in this problem. So we have to understand this thing, that potential is a scalar quantity and it doesn't depend upon the configuration of charges. I hope you get it. Let's move ahead. Now just think and tell me about this particular problem. Does all charged particles will move from high potential to low potential? High and low potential can be referred as, if we're talking about a point where which is supposed to be at high potential, so you can simply consider it as that high potential is something which supposed to have higher electric field, whereas low potential is something which supposed to have almost negative electric field because of negative charges sometimes. Like just think and tell me what it is going to be.
It goes from high to low.
It goes from high to low, but the question is, does all charges move from high to low?
I think yes.
See, high potential generally refer to that there must be some positive charge. Whereas if we are talking about low potential, it must be like that there must be some negative charge. Now let us just place the two charges, positive Q and negative. If you just look at these two charges which we have placed, this positive is going to repel this positive charge, so it will move towards this. Whereas this negative will repel this negative charge, so it will move towards this. So not all the charges move from high potential to low potential, but only protons or positive charge move from high potential to low potential. Whereas if we talk about electrons, that is negative charge. Remember these points is a very important point for solving conceptual problems. Whereas electrons with negative charge moves from low potential to high potential. So this is what you have to keep in mind. So the answer to this question is going to be no. Not all the charged particles move from high potential to low potential. So another question we have, this question is very simple. We have given two charges and they are located 16 centimeters apart. The question is, at what point the positive charge on the line joining the two charges is the electric potential 0? Suppose there are two charges, some plus Q1 and negative Q1 separated by 16 centimeters. Question says, at what point electrostatic potential is 0? So let us assume that there is some point P at which potential is 0. So what we can do here is we can consider that from this positive charge, it is at x distance. So automatically from the negative charge, it is going to be 16 minus x distance. Potential is going to be the sum of both the potentials due to both the charges at point P. So it can be written as V1 plus V2. V1 is going to be K Q1 over R1. V2 is going to be K Q2 over R2. If you just look at the problem, Q2 is negative, so I can write K Q1 by R2, R1 must be equals to K Q2 over R2. So K will cancel out K, Q1 over R1 is equals to Q2 over R2. Q1 is supposed to be what? 5 times 10 to the power minus 8 over R1, that is something we have to find. We have just marked it as X, so let us just substitute it as X only. Is equals to minus 3 will become positive as it has moved from one side to another of around the equality over 16 minus X. So 10 to the power minus 8 will cancel out 10 to the power minus 8. If we try to solve it, we'll have 80 minus 5x is equals to 16 times 5 is 80. 5 times x is minus 5x. 3 times x is 3x. So 80 is going to be 8x. So x is going to be 10 centimeters. So 10 centimeters, or this is the point which is supposed to be 10 centimeters away from Q1, at which potential is 0. So this is how these kind of questions will become. And again, this is the important one. This is an important kind of problem, and you will definitely see something like that in your quiz, upcoming quiz. So just keep this point in mind. There is
Okay.
another question. The question says that there are 2 points A and B are maintained at a potential of 18 volts and minus 5 volts respectively. What will be the magnitude of work done in moving 150 alpha particles from point A to point B? So let us just try to look at the relation for potential. Potential is given by work done per unit charge. The question says, what is the work done in moving a charged particle from A to B? So it is going to be delta V times Q, because whenever we are talking about potential, we are talking about change. So work done can be written as delta U, delta V. What is delta V? Higher to lower potential. So we'll simply subtract these two values and we'll get 18 minus 5. So this will give us delta V. Now, what is the total charge? 150 alpha particles. So charge of one alpha particle is going to be charge twice of proton. So 150 times 2 times charge of proton, which is 1.6 times 10 to the power minus 19. If we solve this value, we'll get the work done. Solve it and tell me what it is going to be. And the work done is always given in joules, so here it is going to be in joules. So it is going to be 11,040 times 10 to the power minus 19. So it is going to be 1.1 into 10 to the power minus 15 joules. That is option D. Again, what's important here is you need to understand that what you actually have to find, and in order to find it, you need to remember the relations, all the key relations from its definition as well as from the derivation section. So option D is going to be the correct one in this particular question. And I hope you actually understood that how we are going to solve such problems. Did you get it?
Yeah.
Now, the next topic here we have is what is the relation between electric field and potential. So I'm not going to give you the derivation, but what you can do here is just remember this particular relation. Electric field is negative of potential gradient. This thing is known as potential gradient. So we'll define it as electric field for any region is also negative of potential gradient. Whenever we are talking about gradient term, always remember that term must be divided by displacement or position. So we have considered that there is small change in position due to small change in displacement, that is dx. So potential gradient is going to be dV over dx. So electric field is always negative of dV over dx. Now here we have so many relations obtained from this particular relation only. We can write dV is equals to negative of E dr. So that is another relation. In order to find out any of the given thing, we'll be using this relation only. Even when we are finding capacitance or electric field between the plates of capacitor, we are going to use this relation only. So this is again a very important relation, and we'll be using this relation like a lot, not in this chapter, but also in the next chapter, that is electric circuits. So keep this in mind. Now here's a very small question, not simple question. Let us try to see that what we can do here. So question says that the potential of an electric field produced by a point charge at any point is given by. So we have given the value of potential, which is supposed to be 3x squared plus 5, where x, y are in meters, v is in volt. So this is the relation to potential value. The question is, what is the potential? What is the electric field at this given point? We have to find electric field at this point. So electric field we have to find, but at what point? -2, 1, 0. Now, the difficult or the tough part, electric field is given by negative of dV over dr, right? But here we have given that the particle position is changing for both, or you can say all the three axes, x, y, and z. So electric field is must be given by negative of dV over dx plus dV over dy plus dV over dz. This is important. This is important to understand. As you can see that the potential has only x component in it. So if we just try to substitute it, we're going to have potential in x-axis only, not in y, not in z. Sorry, electric field only in x-axis, not in y, not in z, because there is no such component is present in this relation for potential from y and z. So we just substitute the value of potential. We're going to have dy dx of 3x square plus 5 plus, if we are going to do the same with y and z axis also, we are going to get 0, because there is no what variable in terms of y and z in the given relation. So if we differentiate it, we're going to have 3 into 2, that is 6x plus 0 plus 0 plus 0. Why we are going to get 0 here? Because there is no y, there is no z, but we are differentiating with respect to x and with respect to y and z. Here it is having x, so when we differentiated it, differentiation is given by power will come forward, will apply the chain rule, that is going to be 6x. Now the important part here is what is the unit, or you can say the limit. So negative of 6x, but if we talk about the limit, it is going to be 0 to -2, because we have to find out electrostatic potential intensity electric field at -2, 1, 0. So x coordinate is going to be -2. So we simply substitute the value. So 6 times -2 plus, not plus, it should be negative. When we are integrating and substituting limit, we'll substitute it in this way, that upper limit minus lower limit. Okay, one more thing here. We don't exactly integrated it, we just differentiated it. And when we differentiated it, we'll get that 6x is going to be negative of it. So this is what electric field is. The part is we have to find electric field at this given point. So we'll substitute the values of x point in this, which is going to be -2, which is going to be 12 volt per meter. This is going to be the electric field at this particular point. Again, We have to understand the concept first, that how exactly what we are doing. This is the key relation. If the problem has an equation which says that potential is varying in all the three quadrants, or you can say in all the three axes, so we have to do it for the other two axes as well. So keep this point in mind. This is again a very important point to remember. So next thing here we have is, this is a quite tricky question, a little more calculative one. You can try it at home and let me know. You can also discuss the same with your classmates and let's figure it out that who is studying more. That's all.
Okay.
That is another such questions. I would say that we can skip this one. There is no need to discuss this particular one. Okay, just think and tell me what's going to be the answer for this particular problem. A positive charge particle is released from rest in a uniform electric field. The electric potential energy of the charge. What happened to the potential energy of the charge?
The charge decreases. C.
Charge. We cannot talk about charge here. We have to talk about electric potential. That what will happen to the electric potential of the charge, electric potential energy of the charge. So just think this way. We have to think that how electric potential energy of the charge will change. So
Okay.
electric potential energy, if you think about, so basically it has given that the charged particle is positive in nature and it is released from rest. So if it is released from rest in a uniform electric field, electric potential energy of the charged particle will be. Now just simply think about it. If it is a positive charge, it must be going from higher potential to lower potential, right? So if charged particle is moving from higher potential to lower potential, its potential energy decreases. This is what we have to understand.
Okay.
Again, remember, if there is a unit positive charge and it is released from rest in uniform electric field, so because of the electric field, the charged particle will move in such a way that it will go from higher potential to lower potential like that.
Okay.
And during that case, potential energy always decreases. Why? Because positive charge particle is going to move with the electric field. So it will decrease because the charge moves along the electric field. Whereas if it was negative charge particle, the potential is going to increase as the negative charge particle will move against the electric field. So that is the question and that is the thing you need to understand. Got it?
Okay.
So now let us talk about the potential versus displacement, or you can say potential and distance curve. So as we know, potential is kq over r. If we try to draw the relation with a positive charge, it is going to look like that. Like potential will decrease as r increases in both the directions. Remember this point. Similarly, if we are going to understand it for the negative charge, it is going to look like that. The graphs are very important. We have to understand that how potential will change for both the graphs or vary with distances for both the charges, positive as well as negative. For multiple point charges, we'll use this relation as I already told you. For multiple point charges, net potential is going to be the sum of all the potentials due to possible pair of charges. So the question is, in which zone potential will be zero? So in order to have potential zero for the two system of charges, you have to think about it. This is your homework. You have to think about it and tell me which zone has zero potential. Same problem. Again, a conceptual question. But if you are able to solve this means you have understood each and everything. You don't have to actually solve it. You just have to figure it out that what should be the point where the potential is zero. Or the question is only asking the zone, which zone. So this red zone, the right zone, afterwards negative 4q, the left zone before q. So just think about it and let me know. So we just talked about it. Tell me the correct answer, which is the correct graph, which is the accurate graph.
B.
Think again. You just saw it. For positive charges, it should decrease.
Yeah. So A. No, C.
Look at this one. Now I try to answer it.
C.
Hmm. This one. Now the charge
D.
is plus Q and plus 4Q. They both are same. The nature of charges are same. So how the graph will look like? Think patiently and then answer. It's easy.
It's D.
No, Arnav. For positive charge, how the graph looks like? For positive charge, it goes like that and it goes like that because V is inversely proportional to R. For negative, because of nature, it ceases in the third and fourth quadrant. Now, if you just look at it, positive charge is because of as there is only positive charge, so graph will lie in first and second quadrant only. There is not even a single curve apart from B and C. They have something in third and fourth quadrant. So A and D will not going to be the answer, that's for sure. Now, if we try to understand B and A are kinda same, but the most different thing here is this. This is not going to happen. So C is going to be the again same one, correct one. Again, remember the basics. This is all about potential and potential energy, and these are very important things to understand in order to excel in capacitors. Because all the potential relation are directly being used in capacitors. You cannot go directly to the capacitors without actually understanding what is potential and potential energy. The potential is simply defined as work done per unit charge, or you can say it is the potential energy which can be actually calculated. So let's keep it till here only. In the next class, we'll start with electrostatic, or you can say the equipotential surfaces, and then we'll move towards the capacitance.
Okay.
So make sure you revise each and everything. I'll share the notes and you write as well.